Hello everyone, welcome to the channel Yashpal's Physics Notes. Today we are going to study the topic Theorem of Perpendicular Axis. Now the theorem states that the moment of inertia of a body about any axis perpendicular to its plane is equal to the sum of moment of inertia of body about any two mutually perpendicular axes in its own plane intersecting each other at the point through which the perpendicular axis passes. So what it basically means that here I am writing, it simply means we have to prove that Iz is equals to Ix plus Iy, where Iz is the moment of inertia for z-axis, Ix is the moment of inertia for x-axis, and Iy is the moment of inertia for y-axis. So before proceeding, there are three conditions which we need to satisfy for proceeding the prove the theorem. So I am writing here the three conditions which are necessary. So condition number one is that x, y and z should be mutually perpendicular axis, which means the angle between x-axis, y-axis and z-axis should be equals to 90 degree, which means they should be mutually perpendicular. So here I am writing condition 1, x, y and z-axis should be mutually perpendicular. Mutually perpendicular. Which means the angle between all these three axes should be 90 degrees. Now second condition is that x and y axis should be in the plane of the body. Here we are considering that x and y axis are in the plane of the body. Here I have considered a two-dimensional body where x axis and y axis lie. That is, they lie in a lamina. Lamina is nothing but a two-dimensional body, sometimes we refer to. So here I am writing second condition, x and y axis should be in the plane of body. In the plane of body. For example, if we consider one paper, one thin paper, we can consider it as a lamina body. So in thin paper, there are two directions, x-axis and y-axis, and there is also z-axis which will be coming out of the plane of paper, but we are only concerned with the x-axis and y-axis which lie in the lamina. So here we are considering x and y-axis should be in the plane of lamina. And third final condition is that z-axis should be perpendicular to the plane of body. So see in this figure I have shown that the z-axis is perpendicular to the plane of body. So here I am writing z-axis should be perpendicular to the plane of body. So these are the three conditions which are required before we proceeding to prove this theorem of perpendicular axis. So now we are going to start proving it. So here I am writing proof. From figure we are going to label some things. So here I am writing, suppose lamina is in xy plane. Lamina is nothing but a two-dimensional body. For example, a thin sheet of paper we can consider as lamina. So here I am writing, suppose the lamina is in xy plane. So I have shown in the figure that lamina is in xy plane. Now we have to show what is meant by Iz, Ix and Iy. So here I am writing, let Ix be the moment of inertia be the moment of inertia of body about OX. So see, in this figure I have shown that O as origin, which is along x-axis. So I can consider this as x-axis, this is z-axis, and this is y-axis. So I can show that Ix is nothing but the moment of inertia of body about this OX axis. Similarly, we can show for Iy and Iz. So Iy be the moment of inertia of body about OY, and similarly Iz be the moment of inertia of body about OZ. So see, in this figure Ix is nothing but along OX, Iy is along OY, Iz is along OZ. Now next step we have to prove that Iz is equals to Ix plus Iy. This was our aim. We have to prove this theorem. So this is our aim to prove. Now here we have considered a lamina in xy plane. Now this lamina can be supposed to be made up of large number of identical particles. So this lamina, there are large number of n number of identical particles. Suppose there is one particle which is present at point P, which I have shown with P, which I have shown with blue color dot, and this position is at point P. So I have considered a one particle. Let the mass of this particle is small m. So here I am writing the lamina can be supposed to be made up of large number of identical particles. So in this figure we have considered large number of identical particles in this lamina, that is two-dimensional plane or sheet of paper. So out of these particles I have considered one particle which is present at point P having the mass small m. So I am writing, let a particle of mass m at point P. Now what we are going to do, we are going to find the moment of inertia of this particle which is present at point P about x-axis. So see, there is a particle and we are going to find the moment of inertia of this particle about x-axis, also about y-axis, and also about z-axis. So here, now in this figure, let the distance OA is x, distance OB is y, distance BP is x, and distance PA as y. So we consider the distances as OA as x, OB as y, BP as x, and PA is y. Why we considered? Because you can see this is a quadrilateral. Okay, quadrilateral OA BP is nothing but a rectangle. See from figure, the distance OB will be equals to distance PA. Okay, and also distance BP will be same as distance OA. So quadrilateral OA BP is a rectangle, and we know that in rectangle all angles are 90 degree. All angles are 90 degree. Okay, and opposite sides are equal. Opposite sides are equal. So we are going to make the use of these assumptions which I have written here, that the distance we have considered O as x, OB as y, BP as x and PA as y. So our quadrilateral OABP is nothing but a rectangle which have opposite sides are equal. So now here I have let a particle of mass m is present at point P. Now what we are going to do, here I am writing PA as y and PB as x. See from figure, as I have told you, PA, distance PA is y and PB is x. So ultimately the opposite sides will be of same distance. So now here I am writing moment of inertia of particle P about x-axis. Moment of inertia of particle P, which has mass small m, about x-axis. About x-axis. Now we know that the formula of moment of inertia. Moment of inertia is nothing but the mass into perpendicular distance square. So perpendicular distance square. This is the formula of moment of inertia. Okay. So now in case of particle P present about x-axis, so moment of inertia of particle P about x-axis will become mass we have considered small m and perpendicular distance. See, the perpendicular distance is which line is perpendicular here? This PA is perpendicular to x-axis. So the distance is y, which we have considered PA. So here I am writing y square. Now we are going to find the moment of inertia of particle P about y-axis. So see from the figure, this is the y-axis and BP is perpendicular to this y-axis. So here I can write moment of inertia of particle P about y-axis. So we are going to find about y-axis, which will be equals to I. The formula will be same, mass into perpendicular distance. So mass at point P is considered as, we consider it as small m, and perpendicular distance. So see, the line which is perpendicular to y-axis is BP and value of BP is x. So here I can write m into x square. Give this in equation 1 and this is our equation. Now here I am writing moment of inertia of particle P about z-axis. So moment of inertia of particle P about z-axis, which will be equals to I is equals to, so from figure, see, this is the z-axis and the perpendicular distance is the distance OP, which will be perpendicular to this z-axis. So the value of OP is small r. We consider it as small r. So that's why here I am writing m into r square. So this was our complete figure. We have labeled it and we have named each and every portion of this part figure. Now moment of inertia, here we have find the moment of inertia along x-axis, y-axis and z-axis for this particle P. Okay, for this particle P. Now we have to find the moment of inertia of whole body. So what we are going to do, we are going to use the summation sign to add up all the masses. So here I can write moment of inertia before this, give this as equation number 3. So moment of inertia of whole body about x-axis. So what we are going to do, we are going to use the summation set. So along x-axis means here I am writing Ix and summation. Now what was the moment of inertia of particle along x-axis? It was my square. So here I am writing summation my square. Summation means sum of all the masses along the x-axis. So this will be our equation number 4. Similarly, we can write for y-axis and z-axis. So here I am writing moment of inertia of whole body about y-axis. So here I can write y is equals to summation. From equation 2 we have m x square. So give this as equation number 5. Also moment of inertia of whole body about z-axis will be, from equation 3 I can write Iz is equals to summation, which means sum of all masses, m r square. So give this as equation number 6. Now what we are going to do from figure, see, from this figure we are going to consider the triangle OAP. Here we are going to consider the triangle OAP and we are going to use the Pythagoras theorem in. See here angle A is 90 degrees since we have considered this as quadrilateral OABP as rectangle. So here I am writing in quadrilateral OABP OAPB, angle A is 90 degree. OAPB, angle A is 90 degree. So in triangle OAP. So here I am writing in triangle OAP, angle A is 90 degree. Here we are going to use the Pythagoras theorem. So I am writing here we are going to use the Pythagoras theorem in triangle OAP. So in triangle OAP, you can see that side OP is R, OA is X and PA is Y. So here I am writing in triangle OAP, we are going to use the Pythagoras theorem. So by Pythagoras theorem, hypotenuse square is equals to square of one side, the square of other side. So this is according to the Pythagoras theorem. So give this as equation number 7. Now what we are going to do, we are going to substitute this equation 7 in equation number 6. So here I am writing substituting equation 7 in equation number 6. So our equation number 6 was Iz summation m r square, but here we have already found the value of r square, so I can substitute it directly. M into x square plus y square. Here I can separate out these terms and write it as Iz is equals to summation of mx square plus summation of my square. But we know that summation of mx square is nothing but the I y from equation 5, and summation my square is ix from equation number 4. So here I am writing from equation 4 and 5. We get our equation number 4 was ix is equals to summation of my square. So this equation becomes Iz is equals to Iy plus Ix. Also I can write it as Iz is equals to nothing but Ix plus Iy. So this was our desired result which we have to prove out. So we have proved that theorem of perpendicular axis. Thank you for watching. Please subscribe the channel. Keep watching.